Hello, in this video I'd like to talk to you about some of the forces at a distance that help to hold atoms together to form molecules. But what I'd like to do first is just do a little backup review of some basic information about atoms. So I'm using number 2 helium as our example, and I chose this because it's the smallest atom that has all the parts that we need to talk about. So the first thing we need to understand is the atomic number on the periodic table of elements for helium is 2. What that number tells us is the number of protons that are present in the nucleus, as well as the number of neutrons for our purposes. So we're representing protons with a plus sign because they are positively charged. So I'm going to put 2 pluses in here. And we also have 2 neutrons. This will give us our total atomic mass, minus the minuscule amount of mass that we have for electrons. Now, helium also has 2 electrons, and they're zooming around in this outer orbital, outer shell. Since it's the only shell, these are also referred to as valence electrons. Now, these electrons can zoom all over the place around here, but they stay a certain distance from the nucleus in general in their orbital or shell. They don't go bopping out here and getting really close and things like that. Now, for our purposes today, I'm going to put the electrons beside each other, even though they are very likely not traveling in pairs, just because of the fact that it makes it easier for our representation down below. Now, there's a really cool little formula right over here, 2n squared, where n represents the number of energy shells from the nucleus of the atom. So for example, here I have the nucleus of my atom for oxygen, and I have the first shell or orbital. So I replace the 2 in my formula with a 1. So 1 squared is 1 times 2 is 2. What that tells me is the most electrons I can put in this inner shell is 2. It won't hold anymore. It only needs 2. Now, if I substitute a 2 for the n for the second shell, so I put my 2 into my formula, I have 2 squared, that's 4. 4 times 2 is 8. So ideally, if I have an atom that has 2 shells, it would ideally like to have 8 electrons in the outer shell. Now, this isn't always possible, and this is why atoms, such as carbon and oxygen, bond together so well to form the molecule carbon dioxide. So let's go through and take a look at this. All right, so in my first orbital for here, I can have 2 electrons, and I have the electrons paired together. Well, that's great information, but the problem is I need to know how many electrons total do I have for each of these atoms. So that information is displayed up here for you. So carbon has 6 electrons total. Oxygen has 8 electrons total. So let's see how that works for filling up the shells. So for carbon, I can have 2 electrons in the inner shell, so I have to start by filling the inner shell first. But if I take 6 minus 2, that means I have 4 more electrons. So I'm going to put those other 4 right here and right here. Now, if you notice in our model, these are not touching each other. These are force at a distance arrows. These electrons are held together by an electrical force. They're not held together by direct contact. It's kind of important to know. Okay, now we have oxygen. We have 2 oxygen atoms represented because we have carbon dioxide. So we have 8 electrons. So again, the first orbital can hold 2. So we'll put 2 in the first orbital. And then if we take 8 minus 2, we have 6 electrons left. So what we're going to do is we're going to put those around here. And then we're going to do the same thing for the other side. Now, if you look at this, what happens is we have 2 valence shells, or 2 orbitals. The outer orbital wants to have 8 electrons. Now, on their own, none of these have 8 electrons in the outer shell. This one has 6 for the oxygen. The carbon dioxide, or I'm sorry, the carbon only has 4 in the outer shell, and this oxygen also only has 6 in the outer shell. But when we have these together and we have this force at a distance working where they are pulled together instead of as 3 individual atoms, they are now acting as a molecule, look at what it appears to be. It appears as though the oxygen now has 2, 4, 6, 8 electrons because it's sharing electrons with carbon. The carbon now appears to have 2, 4, 6, 8 electrons because it's sharing with both oxygens, and this oxygen appears to have 2, 4, 6, 8 electrons also in its secondary shell or its valence shell. So what happens is, this is a very stable molecule. To disrupt this molecule, we have to add a lot of extra energy to break up the carbon dioxide. And that, ladies and gentlemen, is how this is working.